Okay. Oh. Oh.
Start. We have decided to, can you hear me? Yeah. Hi, everyone. So we have decided to swap the speakers. Pierre Levy will go first and Louis Lamb after, due to technical issues, the usual ones. So let me get going without further delays. My name is Arthur Garcés, and it's a great pleasure to introduce Pierre Levy, philosopher from the University of Montreal, also intellect metadata. And Pierre is very, very well known for having written many books. These books have been translated to 12 different languages. I will just mention 2 or 3. The Semantic Sphere, which is the latest one. Collective Intelligence. IJCLR’22 NeSy’22. So these are some of his very popular books. And today he will talk to us about a protocol for semantics, which is highly relevant to the research in neurosymbolic AI as we look at semantics of such systems. It's a great honor. Thank you so much for agreeing to give a talk.
Okay. Thank you, Arthur. I'm very pleased to be with you this afternoon. And I would like to thank the organizer, Stephen Muggleton, and also Arthur and Louis Lamb, who probably proposed my name. The topic of my communication will be a language that I have invented. And this language has the same expressive power as a natural language, but at the same time, it is a mathematical system. It is an algebra, a mathematical category. And the goal of the language is to make semantic computable, semantics. And I will explain a little bit later that semantics is something that is very complex, very broad. What I want to do is to make linguistic semantics computable. Okay. So first, I'll go to the next slide. Probably, oh, no. So this is the, no. Okay. And this is the good. And first, a little bit of context. I'm a philosopher. And as such, I am interested in the problem of meaning. Okay, and it's a very long tradition. And I'm sorry, I forgot, these are my great ancestors. I forgot Leibniz here because Leibniz too was trying to compute on concepts. So it's a very ancient project. So what is meaning? How does it work? And I could even add, where are we now in the endeavor of the mathematization of language and on the calculation of concepts? So this is my initial questions. Then another aspect of the background is more related to history, to our current period. In the early 90s, I understood that the internet would be the main communication medium for our species. And also I was convinced that the growth of computing power and its availability would augment language and cognition, exactly like writing, printing, and electronic media revolutions did previously. So it was a reasoning by analogy. And also, even before the advent of the web, I understood, because I had the luck to be in a laboratory where people were studying hypertext. I understood that dynamic hypertext would be the future of text. And finally, what was the most important for me, I understood that there will be a common digital memory that will be accessible for everybody, and that it will be the basis for a new kind of collective intelligence, let's say a large-scale collective intelligence. So if all this was true, I thought that we needed a unifying semantic coordinate system. And this semantic coordinate system should be a language, but a digital native language, a language that would lend itself to calculation and programming in order to explore and to exploit this memory together. Okay. So there was, I met the problem of the mathematization or the computation of semantics. So now I have to explain a little bit, what do I mean by semantics? And this is rather tricky because generally linguists and computer scientists and sociologists don't have the same definition of semantics. So there is a problem of the semantics of semantics. I distinguish at least 3 layers of semantics. I say layers because everything is happening at the same time, simultaneously. There is a pragmatic aspect where the meaning of my speech is the effect that it has on a social situation. And here it is about relevance. There is a referential semantics, and generally computer scientists are more versed into this semantics because this is about the relation between a proposition and a state of things. And truth, of course, is the correspondence between the two. And when we are speaking about induction, deduction, abduction, and so on, generally, we are referring to this kind of semantics. But what I am speaking about, what I will speak about now is linguistic semantics. And this is about the conceptualization. And this linguistic semantics comes from the meaning of words and the way these words are combined according to grammatical rules. Okay, and I am uttering a sentence, and it evokes in your mind a particular scene or a particular representation. First, it has to do this, and then you can look if it's related to a reality, and then the effect it has on a particular social situation. So, I am speaking about linguistic semantics. So in this regard, I said that my language has the same expressive power as a natural language. It means that you can create complex sentences. You can do causal modeling, you can do reasoning, you can do a lot of different kind of explanations. You can create new concepts, and as it is the case for any natural language, you can translate any other natural language. This is the power of a natural language. But it has also a computable semantics. What do I mean by computable semantics? Okay, this is a little tricky. It means first that given a sequence of sounds, there is a translation of this sequence of sound into a network of concepts. Exactly. I am not transmitting directly to you a sequence of concepts. What you are hearing are just sounds, but you are reconstituting in your mind a network of concepts that makes sense. And of course, it goes both ways. This is the way language works. So in IEML, there is an automatic decoding between the sequence of sounds and network of concepts. And also, you have algebraic functions or algorithms, if you want, to generate and to recognize concept networks. So you can decompose this. You can generate concepts by using functions, and you can also generate relation or links between concepts by using function or algorithm. And this is, of course, very useful in the field of ontologies, knowledge graphs, data models, domain-specific languages, and so on. I have worked on this project since, I'm a little bit ashamed of saying this, more than 25 years. So I am very happy to say that now the language exists. So there is a dictionary of 3,000 words, and there is a completely regular generative grammar. And also at the level of the implementation, there is a parser. There is a small declarative programming language to generate the conceptual nodes and the links, and there are all kinds of useful features in this editor. Now I'm going more into details. First, I'm going to explain you how I built the dictionary, the words, and then I will explain to you how it is possible to create sentences and relations between sentences and words and conceptual nodes in general. Why only 3,000 words? For two reasons. From the machine side, I wanted to make it easier to compute. So it has to be a limited number of primitives. And on the human side, it is better for cognitive manageability if there is not too many initial words. Okay, to give you an example, there are roughly 10,000 ideograms or Chinese characters in the Chinese writing. And these words are organized in paradigms. A paradigm is roughly a semantic field, and where you have all the possible alternative words to describe a field. For example, the colors or the social roles or things like this. Okay, and this is an example of paradigms. Of course, I am not making the list of all the paradigms of the dictionary. I will give you the address, the web address of the dictionary. You will be able to look by yourself. So, how do you create a language? Okay, I'm going to explain a little bit the creative process that I followed. I had to start from primitives, okay? So from semantic primitives. And in fact, there are, in this language, 6 semantic primitives and only 6. And any expression of this language is a sequence, a punctuated sequence of these primitives. So the first concept that is represented by the letter E means emptiness. It could mean zero, could mean silence, could mean blank, could mean noise, like the opposite of information. Okay. So basically it's nothing. And then you have a duality, virtual and actual, or abstract and concrete, or transcendent and immanent, or the soul and the body, and so on. The yin and the yang, the earth and heaven, and so on. So the basic duality. And then you have the basic ternarity. The prompt for this basic ternarity was the semiotic triangle. So the sign, the interpreter, and the referent. Okay, but it could be, for example, the syntax, semantics, and pragmatics. It could be the legislative, the judiciary, and the executive. You have a lot of ternarities that are rather universal. Or it could be in the field of logic, for example, a proposition, judgment, state of things. Okay. So these semantic symmetries, I did not invent them. I have collected them and I have compacted them. Okay, and what is important to understand is that thanks to the grammar, the generative grammar, we are able to make multiplication and additions in order to create higher order symmetry, for example, symmetry 4, symmetry 6, symmetry 9, and so on. Okay. So there are 2 generative grammar, one to create the words and one other to create the sentences. So now I am speaking about the generative grammar to create the words. Okay, so the words are constructed always in paradigms. It's a kind of multiplication table. And in IEML, every word belongs to one paradigm and one paradigm only. So there is a morphological function. This means the function creates words. This is a linguistic term. And this function combines a multiplicative operation and an additive operation. The multiplicative operation has three roles: the substance, the attribute, and the mode. And of course, as it is the multiplicative operation, it is recursive, and also it is non-commutative. You cannot, when you exchange the place, it does not have the same meaning. And this, I'm not going to explain these paradigms, just to show you the visual aspect of it. And I'm going to show you some other paradigms. So you have a translation in natural language. This is in English, but there is also translation in French, and you can have translation in any other natural language. And you have the IEML expression. In general, the letters represent positions in symmetry systems, and there is a kind of parallelism between the symmetry of the signifieds and the symmetry of the signifiers, or if you want, the syntactic symmetries reflect the semantic symmetries. Okay. And the punctuation mark represents the multiplication layers. Okay, so I had my 6 primitives, and how do I build new concepts from my primitives? So the constraint here is to build concepts that will be used to build other concepts. So you have to create the concept that will be the most conducive to the further construction of other concepts. Okay. So for example, well, in this paradigm, this is the function that is creating the paradigm. So you have S plus B plus T multiplied by S plus B plus T multiplied by E. E is emptiness, so it is not, you see, at the third place, there is always E. So this is a constant in this paradigm. I began to play with the primitives as if they were building blocks. Okay, so I combine, for example, sign with sign. So when signs interact with signs, it's like imagination, inference, interpretation, thought, reflection. Okay. Then I combine sign with being. Okay, I am a being, I receive a sign, I interpret it, I express myself with signs, language. Now, interaction between sign and thing. Okay, the sign is inscribed into the thing, it is reified, it is memory. Society, how did I came to this concept? Beings are gathering together around symbols. It can be a flag, it can be music, it can be knowledge, like we are doing now, etc. And they are making people are making society. And for emotion, it's being in relation with being. So it's an intimate relation, being with itself, with others, and so on. So it is the emotion, and so on. Okay, I'm not going to them, but it's a reasoning by analogy, and it has a certain level of literary creativity. And okay, what I just showed you before was, you can see the blue spot. I made all the multiplication. For example, if I look to the yellow part, virtual sign to know, virtual being want, the intention, a virtual thing I can. But if it is actual thing, I do. Actual being, I commit. Actual sign, I express, and so on. So this is this kind of reasoning, and you can see the the function here. Now, I just wanted to show you the function that is generating this paradigm. It is the letters that we have already seen. Okay. And let's make a little zoom. For the columns, the first column is about knowledge. You can see that there is a Y at the second place. The second column is about intention, want. You can see the O at the second place. The third column is about skills, because it is can. The fourth column is about different kinds of signs. The fifth column is about different kinds of social roles. And the sixth column is about different kinds of techniques, tools, technologies, because it's I do. Okay, and for each column, there is a kind of declension corresponding to reflection, language, memory, society, emotion, world, truth, life, and space. So you see the matrix. Now let's make a zoom of this on this fifth column. And okay, you have 9 social roles that, so you know, it is this letter is the placeholder for the social role, and there is a declension. So this, the interpreter corresponds to the thought. This corresponds to the language, the scribe to the memory, the leader to society, the parent to emotion, the judge to the balance of the world, the researcher for truth, the healer for life, and the guardian for space. So to see the way it is constructed. Just to tell you, these are not the only words to describe the social roles, because there is also another paradigm with 81 cells that make further differentiation in different kind of social roles. Okay. So here I am showing you a little excerpt of another paradigm. This is the paradigm of scientific disciplines. It's a very big paradigm in the dictionary. So you have the scientific disciplines, the objects of these disciplines, and the specialists that are working in this discipline. So the paradigm gather all these things. You can see here that the first row is about philosophy, and it begins by S. The second row is about language and communication. It begins by B, which means language. The third row is about history, and it begins by T. You can see that the first column is about science, the second column is about politics, the third column is about economy, the fourth column is about communication, and so on. Okay, technology here. And okay, technology, you have I. Social science, you have A. Communication, you have U, and so on. So there is a systematic correspondence between the semantic symmetries and the syntactic symmetries. And this is the only way to make semantics computable, of course, because computers can only recognize the signifiers and do not understand the signified. So if you create a correspondence between the two, you can make computer understand the semantics. So I am stopping here for the dictionary and the words, and we are going to speak about the sentences, because of course the words are here to be used in sentences. So the function to create the sentences has also a multiplicative operation and an additive operation. So the multiplicative operation, in this case, it has 9 rows. The first row is the root, generally the verb, but in the case of a noun phrase, it can be also a noun. And then you have a role that corresponds to the subject in traditional grammar, a role who corresponds to an object, a role who corresponds to a recipient. For example, I give something to someone. And there are complements. One is about causality, one about time, one about place, one about intention, and one about manner. Okay. So you can, with this kind of grammar, you can express anything you want. For example, here in a house, a mother tells a story from a book to her child with love among joyful laughter before she falls asleep. Okay. Every sentence is made of 4 parts. One part is the concept, and it begins with a hash. One part is the flexion, and it begins with a tilde. For example, here for this verb, we have a mood, and a tense. Okay, and for the nouns, you have flexions for genders, number, articles, and so on. There is also auxiliaries or cases to precise the different roles. For example, the role time, it is precised by before. It could have been after, for example. For the place, it is in. It could have been out of, and so on. And you have also junctions, for example, and, or, but, because, etc. Okay. So just to give you an idea of the degree of nuance that you can attain with IEML, you have 80 different inflections, more than 100 auxiliary to precise the different roles, and you have 29 junctions. So you can really say everything you want, and remember also that the concepts can be words, but it can also be sentences, and because it is recursive, you can express a concept by using a sentence, and this sentence itself can use another sentence, and so on. It is practically infinite. Well, now you can use this language to index data. Okay. So as the language is only made to express general categories, so anytime that you have a proper noun, for example, you put it as a reference. And this is the reference. For the reference, we use angle brackets. So it can be a number, it can be a URL, it can be any kind of data. And also you can make reference to expression of the language itself. So the language is self-referential. So you can have explanations, and ideally the dictionary can be, any word of the dictionary can be explained by sentences in IEML. You don't have to use natural languages, okay? And now, how do you create links? So a link basically is a sentence with variables or with arguments. For example, in this case, A is the contrary of B. So the word A signify the contrary of the word B. So I use this sentence to describe the meaning of the word in the dictionary. Of course, this kind of relation can be applied to a lot of different concepts because you have a lot of possible contrary. So you have a function to precise the domain of the arguments and the condition that must be verified to create the link. What is important here is that you create a semantic link with syntactic conditions. Okay, that's from a theoretical point of view, that's what is interesting for me. And a second remark, you don't create the links one by one, because, for example, this link create the link to the left is the contrary to the right, and on the top is the contrary on at the bottom, and so on. If you have well constructed your paradigm, you can create 25 links with only one function or more. Okay. And finally, I said that you can create not only links automatically, but you can also create nodes automatically, conceptual nodes. For example, I was working on an ontology of mental health, and you see, for example, here it's the paradigm of perception issues. So for the role 1 and for the role 2, there are variables, and the variables are between braces. So you see hypersensibility, impairment, pain, illusion, hallucinations, etc. And it is applied to all the different senses, and it creates automatically the paradigm. Okay, so it's not only the words that are created in paradigms, but also any concept that you can create with sentences. So now let's recap. So first, it has the same power as a natural language. You can describe anything you want. There is recursivity. You can tell fictions and so on. There is also a dialogic aspect. You have possibility of reasoning, and you can translate other natural languages. And finally, there is everything you need to index data, including the language itself. So the same power as a natural language. But at the same time, it is a mathematical language that allows you to make calculations. Okay. More precisely, it is a category. So you have an algebra that is basically applied to text, completely linear text. So you have operation to write, read, and so on. It is a ring because you have the multiplicative and additive operation. And this is all about change of characters. But each chain of character translates into a complex network. First, the syntactic tree, and this syntactic tree is crossed by paradigmatic matrices. Okay, so this creates an interesting kind of network that I call a rhizome. Okay, and from this category, you can also create functions to automatically generate relations, semantic relation between concepts. So is it the end? Okay. Okay. No, I think that, well, I would like to say two slides, okay? The first slide is about semantic interoperability. What do I mean by semantic interoperability? Semantic, the meaning, communication of meaning, and at the same time, computation on meaning. This interoperability is not about format, like in RDF, for example. It's really about the concepts and the architecture of concept. And it can be used in any format that you want, but it's not a format, it's really a language. And the main idea is that it is not a universal ontology. It is a language that allows you to create as many different ontologies as you want, and they are all interoperable because they are created with the same dictionary using the same language. So that is the main idea. And now, because we are here, so from neuronal AI, I think that we can use IEML for labeling and annotation. It will help it will create a more effective machine learning with more transparency, more explainability, and more ability to generalize. Also, for symbolic AI, it's not only that you can create automatically the nodes and the links, but also that the meaning of the concept are not determined by URIs or by rigid designation in a referential way, but as in natural language, as for example in a dictionary, where a concept is defined by other concepts of the same language. And I think the main benefit for AI will be logical decompartmentalization, a better integration between the neuronal and the symbolic aspect, and also the possibility to accumulate and recombine knowledge in a fluid way. Thank you very much for your patience.
Thank you. Thanks very much for a fascinating talk. The IEML seems to be a generative language for generating new concepts out of old. So have you ever surprised yourself by coming up with a concept which is not readily expressed in English or French, something brand new?
Exactly. That happened a lot at the beginning, because at the beginning of the creation of the language, I created the words in IEML first, and then I was asking, to what do this correspond in French or in English? So I had to find approximation in natural language, but sometimes there was nothing. So you are perfectly right. It was one of the problems that I met. Yes.
That sounds like an opportunity, not a problem.
No, because I wanted to fill every cell. So I always came with an approximation. But for example, let's say, okay, for this one, it was very difficult, frankly. So, because the substance was being, the attribute was sign, and I had to add a plurality that was not there to give it a real meaning. Okay, but for me, this paradigm is important, because if you have a metaphysics or a philosophical system, any philosophical system, you can always start from one or several of these concepts. They are all there. Yeah, I wanted to exclude nothing. This was one of the constraints.